Okay, welcome back to COIC 2325. This is Computer Organization, Chapter 2, Part 1. In this section, we're going to cover two topics, some general concepts about the 86 processor architecture and the Intel 32 processor architecture, the 32-bit processor. So these are all the topics in this chapter, and we're covering these first two topics in this video. So assembly language is a tool that we use to learn how the computer works, and to be able to know that how it works, we need to know the workings of the computer hardware. And so in this chapter, what you're going to be learning is going to help you with programming in assembly language. Okay, so to give you a nice wide view, this would be a motherboard, and a motherboard, on top of the motherboard we have the central processing unit. So this is the socket that would nice, tightly and snugly hold your central processing unit, okay, the CPU. If you've never built a machine before, a computer, I suggest doing that just as an exercise, maybe not in this class, but at some point, just to build your own computer is a nice thing to do. And if you don't like hardware, you don't plan to work with hardware, is just a good experience to have. So this is a close look at the CPU. We're going to talk about the pins on the CPU, and I think in this little picture that I took from the internet, you can see the pins that directly go into the CPU socket. And through these pins is where those ones and zeros that we keep talking about, how the data is transferred. So this slide here talks about the different parts of the CPU. We call it the basic microcomputer design, and sometimes people will call the CPU a microcomputer, or they'll say CPU or processor or microcomputer. And when we look at the CPU, we see that it contains some registers. When we program in assembly language, we'll be programming these registers right here. And this is just limited storage in the CPU. And then, of course, we know that the CPU processes all the data, so we call this the brain of the computer. It does all the calculations and logical operations. The CPU has a clock, and this clock is a high frequency clock, and it helps, and we'll talk in more detail about the clock, but it synchronizes the central processing unit's operations with other system components. So it helps to synchronize those operations. Then the CU, the control unit, coordinates sequence of execution steps in executing machine instructions. So the control unit is the one who coordinates the instructions in your programs, the machine instructions. And then ALU performs the arithmetic and bitwise processing, so it performs arithmetic operations like addition and subtraction, multiplication, division, etc. It also performs logical operations like and, or, and then bitwise just means that it manipulates bits. So it manipulates the ones and zeros. So these are the different parts of the CPU. Then we're going to look at this into a little more detail. Here's your memory storage unit, and the memory storage unit is your like your RAM, and then you have your input-output devices. We're going to talk about the different buses that transfer data and addresses between all these devices here. So here's a closer picture of our CPU. Here's main memory. So main memory, it directly accesses the CPU, and it does this through buses. So a bus, when we talk about computers, a bus is just a collection of wires through which data is transmitted. So I want you to think of how we have different buses. For example, we have buses that take children to school. We have buses that take people to work. We have buses at airports specifically to take them to their terminal. So the computer has different types of buses also, which we'll look at in the next slide. And just like a bus that carries passengers, there's different size buses. So there's big buses that carry lots of kids to school, and some small buses that might carry 20 kids to school. So these buses, depending on how big the bus, it's depending on how many bits of information it can transfer. So if you look at these lines here, and they're called lines, like in computer terms, not just because it's a line, but a collection of lines. So right here, these 3 lines would be one bus, and each line can only transfer 1 bit at a time. So if we have a 16-bit processor, then we would have to have 16 lines to be able to transfer data and transfer addresses. So we would have one bus that transfer data of 16 lines, one bus of 16 lines and transfers addresses. And we'll talk about the different types of buses, but so each bus would have 16 lines. If it's a 32-bit processor, we'd have 32 lines. 64, we'd have 64 lines. So the size of the bus is its width, and that's how many lines and how many bits it can transfer at a time. So of course, the more bits we can transfer at a time, the faster the transferring of data happens. And then the speed of a bus is measured in megahertz. In this slide, we look at the 3 types of buses. So we have an address bus, a data bus, and a control bus. So let's start with the address bus. So buses can transfer data either unidirectionally or bidirectionally. So uni means one way, bi means 2 ways. So the address bus, notice that it has only one way that it's going. So the address bus goes from the CPU to RAM. The CPU sends a memory address along the bus from the CPU to memory. And it does that either to fetch or to write data. So it sends in let's say that I want to get the value of something in an address, then I would set instructions. So CPU sends instructions to RAM and says, give me the data that's in this address, and it passes it that address. Or maybe it wants to write to the address. So it sends RAM the address so that it can write the new piece of data in RAM. Then the data bus is bi-directional, so it goes both ways. It sends the actual data, so the actual, let's say that in the address FFE0, in that address we hold the number 10. So the actual number 10 gets sent through this bus, and it can go both ways. So the CPU can ask for that value, or RAM can send that value to the CPU. And then we have the control bus, and what the control bus does is it carries commands. By the way, the address bus and the data bus, so these right here, if you have a 32-bit processor, then it transfers the addresses and the data 32 bits at a time. That's how many it can transfer at a time. So we would have 32 lines for the first bus, 32 lines for the second bus. And then the control bus it's like if it's a 16-bit processor, your control bus is not going to have 16 lines. The control bus carries commands from the CPU and also status messages to hardware devices. So the control bus for each line does something separately. So it could be just a 4-line bus, and it would send either a 1 or a 0 through the bus, just letting the hardware devices know, oh, I need you to stop. Like maybe you want to make the hardware stop, or you want to write to it or read from it. So it's a little bit different than these right here. The data bus can also, of course, not just transfer information, and the address bus not just transfer information to RAM, but it can transfer information to other input-output devices. But right now we're just looking at these. But these right here will transfer data also to other devices. Something that I suggest that you do is, write down what are the different types of buses. What do they do? Are they one direction, two direction? So draw the different charts, and to help you remember what are the names of the buses, what do they do, and what are they transferring, how much, etc. Okay, so in this slide we're looking at the clock, and like we said before, it's a clock that is helping synchronize everything in our system. So it helps to determine the speed of the CPU, as it is considered the basic unit of measuring how fast an instruction can be executed by the computer processor. So again, the clock has a cycle, and that cycle determines the speed of the CPU. So sometimes to execute one instruction, it could take 1 clock cycle, or it could take 4 clock cycles. The more clock cycle it takes, the slower it is. And it's the basic unit for measuring how fast an instruction can be executed by the processor. The clock speed of a processor is measured in hertz, which is clock cycles per second. So hertz equals clock cycles per second. So if we say it's 4 hertz, there would be 4 clock cycles per second that it takes to for that one instruction to process. A CPU which completes 3 billion, a CPU which completes 3 billion clock cycles per second. So 3 billion clock cycles per second has a clock speed of 3 gigahertz. So if we are measuring how fast an instruction executed or processed, then we would say, we would actually say like 2 gigahertz or 3 gigahertz, but it would mean 1 gigahertz would be 1 billion clock cycles per second. Okay, a single machine instruction doesn't just magically execute all at once. There are some steps that happen, and this is called the instruction execution cycle. So the first step is to fetch the instructions. So the CPU fetches the instructions from memory, and there's a queue of instructions. So which instructions does it need to fetch first to then go to execute? So there's a queue, just like a queue is like a queue on a printer. The first thing you print is the first thing that gets printed. Same thing with a queue of instructions. The first instruction is the one that gets processed first. So we fetch that instruction, and then the CPU decodes the instruction by looking at the binary patterns. If the instruction includes an operand, like an input value, remember operands are like, if you say A plus B, A is an operand and B is an operand. So if it involves input values, then it fetches those values, and then it executes whatever the instruction is. If the instruction is to store a value, an operand, then it's going to store. So this step here happens only if you have input values, and this step here happens only if you store, if your program is storing something. So the main steps of the instruction execution cycle are to fetch, decode, and then execute. Reading from memory. Multiple machine cycles are required when reading from memory because it responds much more slowly than the CPU. So we do have some registers in the CPU, and to read values from those registers is going to be a lot faster than reading from RAM. So the steps to read from memory are: place the address of the value you want to read on the address bus. So remember, we talked about the address bus. So the CPU is going to give RAM the address that it wants to read. Then we assert the processor's read pin. So we change the value of the processor's read pin, and we wait 1 clock cycle for the memory chips to respond. Then we take the data, we copy the data from the data bus. So the data bus is now going to return the data from that memory location, and the CPU will put it into the destination operand. So whatever it was. So for example, if you say A equals 10, then we first have to get the address of A. So CPU says, RAM, give me the address of A. RAM sends it through, sends the address, the CPU sends the address to RAM of where A is, and then RAM sends back the 10. and then it does whatever it needs to do with that value. Okay, in this slide, we're going to talk about cache memory. And there is a video. If you download these slides, you can play the video. And it'll talk a little bit more about cache memory. But cache memory is a high-speed, expensive static RAM, both inside and outside the CPU. So cache memory is not your main memory. Cache memory sits either inside the CPU, like on the CPU, embedded in the CPU, or it's very close to the CPU and is accessed with really high speed bus. And the reason for cache memory when this was added is because when we get data from our main memory, it does take a little while. It's fast, but it does take a while to access that memory. With cache memory, it keeps your instructions that you use the most and you access the most are kept in cache memory. So the CPU doesn't have to travel as fast to get those instructions and data, and can just very quickly process those instructions and data. So cache memory, you can think of it like when you open a document, and maybe you use that document every day. It's a document that you use every day. So that document that you use every day will be in your recents. And you don't have to go down 1, 2, 3, 4 folders deep to find the document. It's just going to be quickly in your recents. You see it, you open it, you get access to it quickly. That's how cache memory works. And there's also a level 3 cache, which is not as fast as level 2 or level 1, but it manages the level 1 and level 2 cache. The level 1 cache is the fastest, again, because it's embedded in the CPU, versus level 2, it's close to the CPU but not embedded in the CPU, and uses very high, it uses a bus that can transfer data very fast and instructions. Then we have these two terms, cache hit and cache miss. Cache hit just means CPU went to look for the data, to read it, and it's in cache memory. Cache miss is when it's not in cache memory. This is a slide of how a program runs, just a basic view. So we start here with the user. The user sends a program name to the operating system. So go find that program and open it for me. So the operating system is going to search for that program in the current directory. And if it finds the program that it wants, that you want to open, then it goes and it gets the starting cluster from the directory entry. So every time that you have a program running, we call that it's a process. So each thing running on your machine is a process, and there's a directory that has how big the program is, the address that it can be found of that process. So this process is running here, and this is how big it is. So then we load and we start the program. And then when you load and start the program, it goes back to the operating system. And I'm just reading my notes that I have over here. So the operating system begins execution and assigns it a process ID. The operating system then tracks the execution of the process And so the operating system is tracking that process, and it's responding to any requisitions from the program. So it's running, and let's say it's running Microsoft Word, and you say go open file. Well, that's an execution that then the operating system has to go and do. And so it's the operating system's job to track what this program needs. Like I need more memory, or I need to access the disk file, or I need to access an input or an output device. That is what the operating system is managing. Okay, the next section we're going to look at the IA 32-bit processor architecture. This is the Intel 32-bit processor architecture. These are the 4 things that we'll look at for the 32-bit processor architecture: the modes of operation, so different modes that this processor operates in, the basic execution environment, a unit inside the processor called the floating point unit, and then we'll look at the Intel microprocessor history. So here are the 2 of the different modes of operation that processor can operate in. The next 2 will be in the other slide. So the 86 processor has 3 primary modes of operation. The first one is the real address mode. The real address mode is the native MS-DOS. It's useful if a program requires direct access to system memory and hardware devices. And it's not currently supported by Windows. Everything is running in one executable space when we run in real address mode. And we'll talk about what that means in a second. So I don't have there's a mode that we'll look at in a minute that's called protected mode. So here, what's important about this is that when you're in real address mode, everything is running in one executable space. That means that if you have 4 processes that are running, they're all in the same space, same memory space. And if one of those processors, for some reason, goes and writes on top of the address that's running this process, and it's going to crash this process. And so protected mode, which is on the next slide, protected mode segments, and it has a space for each of the processes. So this is why this is not supported by Windows, because we don't want everything running on the same space. Then there's the system management mode. It's a special purpose operating mode provided for handling system-wide functions like power management, system hardware control. It's intended for use only by system firmware like BIOS, but not by application software or any kind of general purpose system software. So this is the system management mode. Here's the protective mode. It's a native mode to Windows and Linux. All instructions and features are available. Programs are in memory segments. So each process that runs is in one segment, and it's not going to go in and write on the other programs that are running. So they're separate, they have their own little houses, and you can't overwrite them. And then you have the virtual 8086 mode. This is a hybrid of the protected mode. It's a hybrid of this. And it's for backward compatibility, meaning like when we came out with the 32-bit processor, we had to be able to run 16-bit applications on the 32-bit processor. So in the 64-bit processor, we have to be able to run 32-bit applications, and that's why this is used, so that we can run applications that were built on smaller processors. Basic execution environment. So in the next few slides, we're going to talk about addressable memory, general purpose registers. So we're going to start getting into registers, which is what we'll use to code in assembly language. Index and base registers, specialized register uses, status flags, floating point, MMX, XMM registers. So addressable memory. In a 32-bit processor that is running in protected mode, a task or program can address a linear address space up to 4 gigabytes. Linear address space means that you have one address after the next, after the next. Extended, it is a 32-bit processor, is extended to 64 gigabytes starting with the P6 processor. So again, it's running in protected mode and can address, the program can address a linear address space of up to 4 gigabytes, but extended to 64 with the P6 processor. Real address mode programs can only address a range of 1 megabyte. If the processor is in protected mode and running multiple programs in virtual 8086 mode, each program has its own 1 megabyte memory area. So if the processor is in protected mode, remember we're running in segmented areas, so each segment has 1 megabyte memory area. Where a 32-bit processor in protected mode has 4 gigabytes, extended to 64. Okay, in this slide, we're going to look at the general purpose registers. So, and I have more details on the next slides. So the general purpose registers are named storage locations inside the CPU. So we saw in the CPU, one of the previous slides, that it has registers, it has the ALU, the arithmetic logic unit, the control unit, and the clock. So the registers are optimized for speed. So the registers are on the CPU. We can access those registers. We can program them using assembly language. So we can actually store data in these registers. There are, in a 32-bit general purpose, in a 32-bit processor, we have 1, 2, 3, 4, we have 8 general purpose registers. Each register, because it's a 32-bit processor, holds 32 bits. There's 8 registers, and this is what they're used for. So the registers are used to hold data. So it temporarily holds data during program execution. The data can include variables, constants, intermediate results of calculations. The registers can hold arithmetic operations. So these general purpose registers are essential for performing arithmetic operations like addition, subtraction, multiplication, and division. And the CPU fetches the data from these registers, performs the operations, and then stores the results back. We can use the registers also for logical operations, data movement. So we're moving data between memory and register, and function, arguments, and return values. So you know how we create functions in our programming languages. those arguments, the things that we pass to the function, and what the function returns can be stored in these registers. So here we show this register is named EAX. That's the name of the register. And when we program, we'll have to, if we want to write something to this register, we'll say, put the value 10 into EAX. So EAX can hold 32 bits. Registers use 8-bit, 16-bit, or 32-bit names. So the 32-bit name is EAX. If you want to use the 16-bit name of this register, it would be AX. So these 4 registers right here are all 32-bit registers. And then if I want to write to 16 bits, I would then refer to AX or BX or CX or DX. And then I can break it down even further into this 16-bit into 2 8-bits, but it's more like saying, it's saying that I want so AX, right? But I want to write to the first 8 bytes and to the last 8 bytes. So L stands for the lower quadrant or the lower 8 bits, and this H is high. It stands for the first 8 bits. So AH writes to these first 8, and AL here. So we use A because that's AX. If it was BX, then we would say BH and BL, etc., for each one of these. So here's just a chart saying these are the 32-bit registers, the names. This is the names of the 16-bit registers. This is the names of the 8-bit registers, the high and the low. C, D, that's just the D there. Some registers have only a 16. Remember how we said that there's 8 registers that we're going to be dealing with, but some registers have only a 16-bit name for their lower half. So the ESI, EDI, EBP, and ESP have only a 16-bit name. They don't have an 8-bit name, only 16. These are some specialized uses for these registers. So EAX is used for accumulating. It's also used for multiplication and division instructions. ECX, and I would think of the A as accumulating. ACX, loop counter, C for counter. ESP, the stack pointer, addresses data on the stack. So think of a stack like you're stacking plates, and we have to stack the address of the data, and we would do that with the stack pointer. And so think of SP as the stack pointer. Then we have the index registers. They end in I, index registers, and they're used by the high-speed memory transfer instructions. And then we have EBP is the extended frame pointer. It's used by high-level languages to reference function parameters and local variables. So SP, stack pointer for the addresses of the data. BP is for the function parameters and local variables. Then we have segments like the code segment, data segment, stack segment, and additional segments. EIP stands again for Extended Instruction Pointer. It's a register in the 86 architecture to keep track of the memory address of the next instruction. So as one instruction is executed, we load the next instruction, the address of the next instruction, so that it's ready to go to be executed. We also have some flags. The eFlags register. The eFlags register stores status and control flags. Each flag is a single binary bit, 1 or 0. These flags provide information about the outcome of arithmetic and logical operations, as well as control certain aspects of the CPU's behavior. And we'll look at the flags in the next slide. So in this register, we can have these flags. We can have the carry flag, overflow, sign, 0, auxiliary carry, and parity. So for example, if we have the sign flag, if the result is negative, then we would flag it here and say the result is negative. Okay, we know what floating point is. Floating point numbers are numbers that have decimal numbers. MMX is a single instruction, multiple data, instruction set architecture. One instruction, multiple data. It was designed by Intel in 1997. It's used for integer operations only. And it defines 8 processor registers. And the registers are named MM0 through MM7. There are 8 80-bit floating point data registers. So 8 80-bit floating point data registers, and they're named ST0 through ST7. They're arranged in a stack. That means that we stack it like plates, and we can pop off from the stack from the top. 8 64-bit MX registers. There are 8 64-bit MMX registers, and there's 8 128-bit XMM registers for single instruction, multiple data operations. Okay, and we're going to stop here for this video. In the next video, we're going to talk about Intel's IA 32-bit memory management. We'll also look at the 64-bit processors, and then we'll stop there with the second video. In the third video, we'll have the components of the Intel IA 32-bit microcomputer and input-output systems.